For decades, pop culture has defined laser weapons as glowing, colorful bolts of light zooming across the screen. The actual physics of modern directed energy looks very different, and the primary driver behind its development is cold, mathematical necessity. Modern battlefields are increasingly defined by high-density swarms of low-cost, highly autonomous drones. These unmanned systems can be purchased off the shelf for a few $1,000s and modified into precision-guided loitering munitions capable of overwhelming traditional integrated air defenses. Using multi-million-dollar surface-to-air missiles to shoot down expendable commercial drones creates a fatal economic imbalance. This chart-topping cost per shot makes traditional kinetic defense a losing game in a war of attrition. Relying exclusively on expensive missiles against these masses of cheap drones leads to the rapid depletion of critical national defense reserves. To survive a saturated drone attack, the defending force must find a way to flip the cost-exchange ratio back in their favor. Directed energy weapons provide that solution through two primary technologies. High-energy lasers, or HEL, concentrate photons to melt a target's physical structure, while high-power microwaves, or HPM, emit intense electromagnetic pulses to fry a drone's internal semiconductor circuitry. These systems bypass the constraints of gravity and atmospheric drag by traveling at 300,000 kilometers per second. Because they are powered by electricity rather than physical propellant, they offer a theoretically infinite magazine depth, limited only by the host platform's fuel supply. By reducing the operational cost of an intercept to a few liters of diesel fuel, the economic advantage returns to the defender. A laser system can engage hundreds of targets for a fraction of the cost of a single interceptor missile. India's pursuit of directed energy began in 1989 with the Kali program, a collaborative effort with the Bhabha Atomic Research Center to explore high-energy physics through relativistic electron beams. This foundational research allowed the DRDO to establish specialized laboratories like CHESS and LASTEC. These facilities are dedicated to maturing laboratory physics into ruggedized weapon systems capable of operating in the dust and heat of the Indian frontier. The first major milestone in this transition occurred during the 2025 field trials of the Mk2A tactical laser. Successfully tested at the National Open Air Range, this 30-kilowatt system is designed to provide an inner-layer defense shield against asymmetric threats. To achieve its 30-kilowatt output, the Mk2A uses geometric beam combining. Instead of a single massive emitter, the system synthesizes power by using high-speed mirrors to concentrate 6 individual 5-kilowatt fiber lasers onto a common focal point. This modular architecture allows the military to utilize reliable, industrial-grade fiber lasers to create a highly mobile weapon system that can completely melt hostile drone control surfaces in a matter of seconds. While 30 kilowatts can neutralize Class 1 drones, stopping high-velocity cruise missiles requires the massive 300-kilowatt output of the upcoming DRDO program. Scaling to these power levels triggers a severe thermal bottleneck. Because high-energy lasers are roughly 30% efficient, generating a 300-kilowatt beam produces nearly 700 kilowatts of intense waste heat that can cause localized melting within the weapon itself. To prevent catastrophic failure, engineers utilize pumped two-phase cooling. This system exploits the latent heat of vaporization, the energy absorbed when a liquid boils, to maintain strict, uniform temperatures across the laser diodes within a margin of just 2 degrees. Even if the laser stays cool, the air in front of it creates a second barrier called thermal blooming. The beam's own intense heat causes the air to expand and act like a negative lens, scattering the laser and preventing it from delivering lethal energy to the target. The solution is adaptive optics. Hundreds of piezoelectric actuators ripple a flexible mirror thousands of times per second to pre-distort the beam. These ripples are calculated to perfectly cancel out atmospheric turbulence, resulting in a razor-sharp spot on the target kilometers away. Success at this scale requires absolute control over nonlinear physics and thermal energy storage. Only by mastering these specific environmental constraints can a laser achieve the energy density needed for strategic interception. Naval destroyers like the Visakhapatnam class are the most viable platforms for 300-kilowatt systems. These ships generate massive amounts of organic electrical power and can utilize the surrounding ocean as an infinite heat sink to dissipate the weapon's waste heat. Future vessels, such as the Project 17A Nilgiri-class stealth frigates, are being built with automated combat management systems, specifically designed to network future energy magazines with long-range radar and missile batteries. Airborne integration under the Sujal concept is more demanding. Engineers must miniaturize these power and cooling loops into aerodynamic pods for the Su-30 MKI fighter fleet, drawing kilowatts from the jet engines while preventing the heat from increasing the aircraft's infrared signature. These efforts indicate a transition toward a broader, networked, directed energy infrastructure. India is building its future naval and aerospace platforms around the specific electrical and cooling demands of the energy magazine. This roadmap aligns with a global shift in military engineering. Regional competitors are already fielding road mobile systems like the LW-30 and testing massive shipboard laser systems designed to blind optical sensors and intercept anti-ship missiles. Programs like Israel's Iron Beam and the UK's Dragonfire have already proven that directed energy can destroy aerial targets at the speed of light for just a few dollars per shot, validating the technology's immense cost efficiency. However, moving from successful field trials to fleet-wide deployment is a decade-long process. Transitioning the 300-kilowatt Durga-2 from a prototype into a combat-ready strategic asset will require years of rigorous testing to ensure reliability in unpredictable battlefield conditions. By isolating the specific engineering barriers of beam combination and pumped two-phase cooling, India is creating a defensive shield capable of engaging supersonic cruise missiles and loitering munitions continuously at the price of a few liters of fuel. This infinite magazine provides a sovereign, cost-effective counter to the evolving realities of asymmetric warfare.